When designing circuits, we often place a 100 nanofarad capacitor close to a chip's power pin. Today I'll explain what this 100 nanofarad capacitor does and why we choose 100 nFefa instead of other values. First, the capacitor placed at the chip's power pin is usually called a bypass capacitor or a decoupling capacitor. Since it serves several functions, either name is fine, so what does this capacitor actually do? The first role is filtering high-frequency noise on the power line. The power plane that supplies the chip usually carries a lot of noise. If we power the chip without a bypass capacitor, the noise may cause abnormal operation. With a bypass capacitor at the power pin, much of that high-frequency noise gets filtered out. So the chip receives a cleaner and more stable DC voltage. The second function is energy storage. For example, if a push-pull output pin drives a load capacitor. When the MOSFET turns on, it needs to charge that load capacitor. Where does that current come from? Without a bypass capacitor, the current must travel from the distant power plane. That can create noise or voltage dips on the power plane. Because charging a load capacitor often requires a large instantaneous current. But if a bypass capacitor is placed at the pin, it supplies that current first. So the power plane doesn't get disturbed. This reduces interference on the power network. The third function is shortening the return path of high-frequency currents. Current always flows in a loop. Where it goes out, it must come back. If the output signal switches fast, the current also changes fast. With a bypass capacitor, that fast-changing current returns through a short local loop. Without the capacitor, the return current must travel a long distance. A longer return path increases ME and can interfere with other components. So why do we usually choose 100 nFefa instead of 10 nFefa or 1F? Let's look at the capacitor's equivalent circuit. It's a resistor, an inductor, and an ideal capacitor in series. The capacitor's impedance depends on the signal frequency. At a certain frequency, called FO, the capacitor looks purely resistive and reaches its minimum impedance. This FO is the capacitor's resonant frequency. When frequency is above FO, it behaves inductively. When it's below FO, it behaves capacitively. For filtering or return path purposes, we want it operating in the capacitive region. Because inductance blocks high-frequency signals, so the signal frequency should be lower than the capacitor's resonant frequency. Here's some real data from a manufacturer. A 10 NF capacitor resonates around 60 MHz. A 100 NF capacitor resonates around 15 MHz. A 1F capacitor resonates around 4 MHz. Most digital chips we use operate at frequencies below 10 MHz. So most power-related noise also falls in this range. So in practice, 100 nFefa is the most suitable value for chip power pins. If the chip runs at higher frequencies, we can choose smaller capacitors. You can refer to the table showing the relation between capacitance and frequency. There are a few placement rules for bypass capacitors. First, place it as close as possible to the power pin. Second, each power pin should have its own capacitor. Third, when multiple capacitors are used, the smaller one should be the closest. For example, if 100 nFefa and 10 nFefa are both used, the 10 NF capacitor should be the closest. That's all for today. Thanks for watching.